Okay, now that we've talked about confidence intervals for the slope of a regression line, we're going to go ahead and talk about the significance test for the slope of a regression line. So I couldn't fit this all on one slide, so I went ahead and broke it up over state plan and then do and conclude. So we're going to test the hypothesis, the true slope of the regression line relating blank and blank is 0 at a blank significance level. So our null hypothesis is always going to be that the slope is 0, and our alternative hypothesis would be that it is greater than 0, less than 0, or not equal to 0. And so typically we decide how we want that based on what relationship we want to see. Does one increase make the other one increase, or does one increase make the other one decrease? So for increase and increase, it'd be a positive slope, which would be greater than 0. An increase and decrease would be a less than a negative slope, so less than 0. And then if you're really just not sure, you can do the two-sided test, which is not equal to 0. And so then we're going to use a t-test for slope if our conditions are met. So our conditions are really the same as last time. We have our linear, our random, our normal, our equal variance, and our independence condition. And so really all the same stuff, nothing new there. So then once we do that, we're ready to compute our linear regression on the calculator. So we can then find the slope, and then we can find our Sx from our one variable stats. We can calculate S by putting the residuals in our L3 and then finding the sum of our x squareds. And then from there we calculate our standard error. So none of that part is new. What becomes new now is this, is calculating our t-value, which will be our b minus our other b. And really, because we're assuming that our null hypothesis is that this is 0, this is really just going to be 0. And so it'll be the b from our regression line minus 0, so really just b, over our standard error of b. And so again, because this ends up being 0 because of our null hypothesis, this is the formula we're going to end up using. And then we calculate the t-CDF by calculating the probability of getting the t-statistic this large or larger in the direction specified, and with the degrees of freedom being n minus 2. And then of course we compare to that original significance level. We always checking to see, is our p-value less than our significance level, also known as alpha. And if it is, then we reject our HO. If it's not, then we draw a line through it and we fail to reject. So on and so forth. So same stuff, seeing it over and over and over again. And that's what we're going to go ahead and try and do with our next situation. So our situation is, do customers who stay longer at buffets give larger tips? Well, Charlotte's an AP Stat student who works at an Asian buffet, decided to investigate this question for her second semester project. While she was doing her job as a hostess, she obtained a random sample of receipts, which included length of time in minutes the party was at the restaurant and the amount of tip in dollars. So this is what we're looking at, length of time in minutes and amount of tip in dollars. So those are our variables. Do these data provide convincing evidence that customers who stay longer, so increased time, will give larger tips, increase of tips? So if it's an increase, we're looking for a positive slope. So here's all of her data right here. So here's our L1 and here's our L2. We want to go ahead and put that in there, and we would go ahead and calculate our information. So I'm going to go ahead and go to my calculator real quick. I'm going to take a look at that calculator. And in my, let's turn it on. We'll go to our stat edit so we can see our list there. And once we have that, I'm going to hit stat. We're going to calculate our linear regression, L1, L2, and we can store that if we want to actually look at the graph. So let's go ahead and do alpha trace. Go ahead and program that in there. And there's our equation. And so we're going to want to write that down. Luckily, I went ahead and put that down right here, our regression equation, which we can see. But for our purposes of conditions, we're going to want to check all of our graphs. So I'm going to go ahead and second stat plot. We're going to do just the scatter plot with L1 and L2 graph and zoom 9. So now we can see the scatter plot and we get an idea, and then we sketch that out on our paper, which we already have right here sketched out for us because I took a snapshot of that from a computer. And then we go back to our calculator and we would do a residual plot. So I'm going to second stat plot. We're going to do a scatter plot again with L1 and our residual list. So we do second stat to go to our residual list. And then we graph. And of course, we're going to have to zoom 9 it. And now we look and we see that good amount of scatter, no trumpeting from side to side, good amount above and below. And so again, showing, hey, this is what our residual plot looks like. And then going to our histogram. So again, second stat plot, we can go to the histogram. Or, so here's a histogram of our residuals. So I have to go into my list and get residuals again. And graph and zoom 9. Once it's done, zoom 9. And so yeah, we can kind of see, looks like a little bit of skewness, but this kind of evens out with that. So if we're unsure, let's go ahead and try maybe a box plot. So let's box plot it. Graph, zoom 9. Looks pretty good. I'm going to turn off that line real quick because it's starting to bother me. Now graph. Box plot. Actually, box plot looks way better than that histogram. So now let's go ahead and do a normal probability plot. So we'll go down to our last one with our residuals. We'll zoom 9. And my only worry that looks pretty linear is this little peak at the end there. It looks like there's a little bit of an issue, but overall it's pretty linear, so we'll call that good. So we've checked all of our stuff. Now we're going to go ahead and answer all the questions we have. So when we did our regression line, we ended up with this. Here's our y-intercept, our a value. Here was our b value, our slope. And now we have to actually write it where we're defining the variables. So our y variable was tip. So this is our tip predicted. So we put the hat on it. So we can predict our tip value by 4.535 plus 0.03 times our x value, which is the time at the restaurant. And so there is our equation. So now we're going to carry out the appropriate test to answer Charlotte's question. So we're going to test the hypothesis that the true slope beta of the regression line relating time spent at the table, which is our x value, and tip amount, our y value, is 0 at a 0.05 significance level. So our null hypothesis beta equals 0. Our alternative hypothesis beta is greater than 0. Why? Because longer time, so increased time, increased tip, means a positive association or positive slope, which is positive is bigger than 0. And then our plan, we go through linear. Our scatter plot shows moderately positive slope. Residual plot shows no pattern or curve. Random, a random sample of 12 receipts. Histogram shows no strong skewness or outliers. Again, the more skewness we have with the smaller numbers, the more we should be concerned because it is a t-distribution. Equal variance, we have even scatter above and below, even distance from zero line. Independent, reasonable to assume more than 120 people visit the restaurant. Then we go to our slope. So when we calculated our regression line, our slope was 0.03. the standard deviation of our x's. So remember how we calculate that? We do the one variable stats on L1. That'll give us this value right here. To calculate s, we need to put our residuals in list 3. And then we do a one variable stats, and we're looking for the summation of x squared. And that gives us the 31.65. So then we plug it into our formula, we get our s, and then we can calculate SEB by taking s divided by the standard deviation of x times the square root of n minus 1. So now we have all of our bits and pieces. We can calculate t, and t is going to be our b divided by our standard error. And that gives us a t-value of 1.2245. So to calculate our p-value, it's a t-CDF, not a 2-t-CDF. So remember, we do a 2-t-CDF if it's a two-sided test, but this is a one-sided. So then our lower bound is going to be our value. Our upper bound is something really big, and our degree of freedom is 10. Why 10? Because in here, our degrees of freedom is our sample size minus 2. So 12 minus 2 gives me that, which gives me the 0.1244. Now that we have our probability value, we ask and we say, hey, let me come back to here. Is this, and this is how I always write it, I take this, is this less than our significance level, which we chose 0.05. And since it is not less than, because 12 is not less than 5, then we fail to reject. Since our p-value is not less than 0.05, we fail to reject our null hypothesis. We do not have convincing evidence that customers that spent more time at a table leave larger tips. So now that we've done that all by hand, we're going to compare this to the computer printout. So the computer printout says, hey, here's my y-intercept, here's my slope, looks pretty right on. Here is my standard error, looks pretty good. And then look at here, oh my gosh, underneath t I get 1.23. What did we get for t? Almost 1.23. Looks pretty darn good. And then the p-value is 0.247. Well, that's off, because 0.247 is a two-sided test. So when we're looking at our computer printouts, we're going to see the t-value and the p-value for a two-sided test. So now with computer printouts, we can actually figure out what is our t-score, what is our probability. In our case, we take this probability and divide by 2, which gets us about 0.12 something, I think 35, with rounding. And so again, giving us the idea of all our information. We can even check our S value, 1.779, 1.779, we're good to go. Everything matches up. So everything matches but the p-value. Unless we divide the p-value by 2. Which means that this p-value is always for a two-sided test. So anytime you want the p-value for one-sided test, you just times by 2. So, key thing. Now I've shown you how to do everything the hard way. We're going to look at how to do this on the calculator. And the reason why we like doing it on the calculator is because it gives us that S value. And you must have data points. So we need to know those lists. And without the lists, we can't actually calculate that. So let's go ahead and take a look at, we've got all of our information in the calculator. So I'm going to quit that diagram. I'm going to go to stat, and I'm going to go ahead and calculate. No, I'm going to tests. And so what I can do is I can do so if we look back, they say a linear regression t-test or a linear regression t-interval. And that works for both of them. So we're looking down for linear regression t-test, linear regression t-interval. So a t-test, L1, L2, frequency, and then we want to say, we think it's going to be positive, so we're going to select greater than 0, and we're going to calculate. And what's nice here is they give us that t-value, they give us the p-value for our test, for a greater than 0 test. They tell us the degrees of freedom. They give me the y-intercept, they give me the slope, they give me that s value. So now, using this test built in, we don't have to calculate s by hand anymore. It gives us r squared, it gives us r. So now when we want to calculate standard error, we've got the information we need. We don't have to calculate s by hand. It gives it to us. And that's pretty much it for this section.